and probably not remember everything. So this is the equation. The wave equation is a partial differential equation. The Fourier transform is, for this example, is only on applied to X, the spatial Fourier transform. And then after you do the Fourier transform, you convert the partial differential equation to this ordinary differential equation and solve that equation for the transform, and then do the inverse transform to get the solution. And it turns out the solution is really elementary, but so this is just like a simple example. All right, it's subject to initial condition y x t equals 0 is equal to f x, and the derivative, time derivative is x 0 at 0. This means take the derivative and evaluate 0. Okay. That's straightforward. Now I do the Fourier transform. You can write down the Fourier transform and inverse transform pair. So you write the y x t as inverse transform using the symmetric convention. It will be integrating the Fourier transform is defined as this. Let's use k instead of textbook alpha. It's really strange to use alpha. Right. And then, but the convention in your textbook, this is again use the minus one, but that's okay. Doesn't matter. This is decay. Get back to this is the inverse transform, and so likewise the transform is just same one minus b. Okay, so this is the inverse transform and transform pair. Okay, and so the initial condition, you can do the same thing to evaluate that as 0. So t equals 0. That just basically just change that to 0. That is just L. So y x 0 equals to L. So the Fourier transform, or the initial condition fx is like inverse transform. This k at 0 also. And likewise, the Fourier transform is y at 0, so it's just L. Okay. The pair is for t equals 0 given by that, except that this definition of the initial condition as L. Okay. So so going through the process, then look at that as taking the Fourier transform of the equation, and then use the property of Fourier transform. You take the square root, basically the transform will put our minus k square on the right hand side, minus k square y t. Right. The left hand side, the right hand side doesn't, the derivative doesn't change. It's still partial derivative, but if you treat k as a parameter, you can write it as total derivative to not get yourself confused. It's not a partial differential equation now, because you treat k as a parameter rather than variable you need to solve differential equation. Okay. Now, that is simple harmonic oscillator, right? So one here is the two solution. I mean, you can use sine or cosine or exponential function. For this case, because you're using Fourier transform, it seems easier to use exponential function. So now to check out the argument. So you multiply v to the other side, and that and take the square, which should be the argument of the exponential function other than t. So we have I k times t. Right? Okay, so that. So multiply v to the other side. That becomes, it looks like this is the angular frequency square. Kv is like the angular frequency square. So the solutions are given by I omega t, right? So you have the angular frequency or minus I. Okay, all follow that. This is ODE, so hopefully you remember that. Okay, and now you want to apply the initial condition, and the initial condition is that you have this one, and t equals 0 is given by this one. But we can use the second one first. The second partial t, right? So partial t is partial y partial t is 0. So it means that if you take the positivity of Fourier transform, and that should also be 0 because 0, the Fourier transform is 0, right? So the partial y, capital Y, t, and value at 0. Let's just pull out the RKV C sub 1 minus C sub 2. That should be 0. And so that this is just to show that C sub 1 and C sub 2 are the same. So that, that may or may not simplify things, but that's okay. So why we can simplify that? Right. That's C sub 1 minus. It's just save a little bit writing. So instead of two unknown coefficient, you have one unknown. Okay, and now you apply this the first one. Right. This is plus. So this is C1 equals C2, C1 plus C2. Right. Okay. Now apply to the first one. This C sub 1, 2 C sub 1. Right. You evaluate 0, this is 1, this is C sub 1. Just two constant equals to equals to this one. Yeah. Right. This is initial value of the y. Right. So that is C sub 1, and you can substitute C sub 1 over here and then get y as a function of k and t. Right. And once you have y as a function of t, you put it back to here and get uh, the solution. Right. So this is an inverse transform. So I mean, you just have to keep doing that, and just need some space. This is a little bit too long. Or maybe I just move to okay. The y xt is square root y. Now I need to be a little careful. Seems like last time I didn't do it carefully enough. So we have e to the I minus I k x k, and the rest is this one with c sub 1 given by this one. Right. So c sub 1, the two c sub 1, so you have a factor 1/2. There's no factor 1/2. And then there's the integration of f. But you already have x, so this probably you can choose another function. Another variable x prime e k x prime x prime, right? And then multiply by the rest. I think probably maybe too much over there. Multiply down. E to the I. E t. And this fx, fx point. Yeah, I did that fx point. But this is just the coefficient. And there's what another graph 2 times effect. That should be all. That should be all. Now you just evaluate the integral, and the integral. There are two integrals. One is dk, one is dx prime, and you can do the k integral because every factor has an exponential function, right? So then combine the k to a single exponential function. They are ik. So this is like another line. So 1/2 of pi and combine all the, so take the x prime, fx prime, x prime out. The rest is dk integral, right? And there will be two terms. One is e to the, get which of, and combine all the exponential factor. We have a ik x prime minus x, and then plus kb. Oh, no, kb, vt. Yeah, we power k, vt, right? And the other term is the same, except the vt change. Plus vt. Okay, 1 minus. 1 minus. This is participant. Yeah. Okay. All right. And these two integrals are what we talk about, the formula that you should memorize. So integrating over this kind of integration, e to the I k, the integration variable multiplied by whatever factor. And you remember that? I have to memorize that. That is from either the orthonormal condition or the completeness condition. You remember that? Those integral, this dk. Each term will give you one. Remember? No. That's one comment. You forget. This is so. That's just e to the I k or x minus x. I think the completeness condition is 2 pi. Right. or either the orthonormal or completeness. For completeness, you interchange k and x, right? But it's just a mathematical result. So this in both of these terms will give you a delta function times 2 pi, so you cancel this 2 pi. So it's one half factor. And there's still an integral. X prime, dx prime. The two factor. One is delta x pi minus x plus vt, and then the other factor delta x pi minus x minus vt. And you know how to integrate this one, the final step, because the delta function, and you can integrate x pi. So the answer is whatever the rest of the integram, evaluate x pi equals to the value such that the argument of delta function is 0. So the first one is x minus vt, the other x plus vt. So it's 1/2 of f x minus vt plus f plus vt. Can you see that? Right? So that will be the answer. I think this is hopefully this answer of the textbook. Where's the answer of the textbook? Yeah, 20.65. Okay, so it take a while, but then you finally get a very trivial answer. So this is, you can guess that because when you learn about the wave equation, you know that any function of the form, either the argument x minus vt or x plus vt, they are the function of the wave equation. And you put it this way so that at t equals 0, you add it up to going back to f as a function of x, right? Because each one give you half of fx, right? We add the two, give you back the initial condition. And when you take the derivative, because you have vt, there's negative sign, there's positive sign. So the total derivative at t equals 0. Okay, so that's a recoverable initial condition. And so we can write down that, almost can write down it immediately without going through all the Fourier transform. But it just shows that the Fourier transform can, in principle, how you apply this to some differential equation, partial differential equation.